Hello, everybody.
Good morning, sir.
Good morning.
Good morning, sir.
Okay, let's continue with prologue. You had a chance to recap what happened last week. Prologue. Hello. Anyway, let's do a recap thing. Okay. So what we were talking about prologue. Prologue is short for programming in logic, and it is a unification-based programming language. Why we are looking at prologue? We are not looking at prologue in a very detailed fashion, but we'll learn some basics of prologue. Why is it important is because just like from functional languages, some ideas from prologue has permeated almost all high-level language these days. Predominantly, the major idea which is there in most programming languages these days is the notion of pattern matching. Okay, you will see what we mean by pattern matching. Okay, so we were talking about prologue, and in prologue I already told you there are two kinds of things. There are facts and there are rules, and what the user inputs is a query, and prologue system tries to prove the query. Yeah, so how does it try to prove the query? It just looks at the facts first and then goes on to look at the rules and try to deduce the query. Let's look at an example. So as I told you, let's try to do a graph system. Graphs. Okay. So in graphs, there are two kinds of things, vertices and edges. So let's try to represent a graph. Let's try to do a graph, very simple graph. And how are we going to represent? We are going to represent the edges of the graph as facts. So let's imagine our graph has let's imagine it has let's imagine it's a graph piece is square. Okay. Square. Okay, what does that mean? That means that we have four vertices, A, B, C, D. Has four vertices. A, B, C, D. Okay. Now, if it is a square graph, then what should be the edges? A to B, then B to C, then C to D, and D to A. Okay. Now, this is a directed graph because every edge has a direction. There is an edge from A to B, B to C, C to D, and D to A. Okay. Now, how do I check if there is a path? What is a rule to describe reachability? What do we mean by reachable? So in this graph, B is reachable from A. I have an edge. C is reachable from A because I can take the edge A to B and B to C. Yeah, just like when we do the reachability in Dijkstra's algorithm. So what is a rule to describe? So let's write a rule to say reach xy, which means that y is reachable from x. What should be a rule? What can I write? Reach xy. Reach xy is obviously true if there is an edge from x to y. Yeah, that is true. If I can have in one edge, if I can go from x to y, then I can reach from x to y. Otherwise, Otherwise, what can I do? I can take an edge from X to some Z, and then if I can reach from Z to Y. Yeah. In this case
So
also.
it should be Y to Z.
Yes, sir.
Y to Z.
Yes, sir.
I didn't understand why is it from Y to Z. Because if I want to reach from X to Y, then I take an edge from X to Z, and Z to Y can reach. Or can I write here Y to Z?
No, sir. This is correct.
This is correct, no?
Yes, sir.
So let's try if it works. So now if I do consult graph.pro, and if I write reach of what are the vertices I should reach from A to X. So what are the places I can reach from A to X? A to B I can reach, B to C I can reach, C to D I can reach, D to A I can reach. So it seems our program is correct. Yeah. And it goes on a loop. Yeah. So but let's not worry about that. Okay. Now, can I write? So first thing we notice is that the order of the above rules is important. To demonstrate that, I'm going to write those rules in a separate way. A reach, okay, it's alternate reach. Alt reach of XY is alt reach of X to Z and edge ZY. Reach XY edge. Okay, if I write it this way, this is also, I mean, if we look at just look at the definition, this is also correct. Yeah, because by definition, if I could reach from X to Y, then if edge of XY axis, then I should reach from X to Y. Similarly, if I could reach from X to Z and Z from Z, there is a edge to Y, then I should reach from X to Y. But if I do this, if I do this, then it is going on an infinite loop. And it says that it went on an infinite loop and then the stack limit is reached. Okay. So it seems like the way you write the rules, the order of the predicates is important. And this has to do with the fact how Prolog is trying to satisfy the rules. Okay. So in order to understand that, we should look at how Prolog is trying to satisfy a given query. Is that clear so far, whatever I said? Saina? No, I don't know. This thing is not okay. All right. Can somebody write what is a E-has triangle? has triangle x, y, z. Um, Question.
But
I want has x, y, z to satisfy this predicate if there is an edge from x to y, y to z, and z to x. So the such a graph I will call a triangle. So how do I write a query for? How do I write this predicate? Has triangle x, y, z forms a triangle. The vertices x and y, x, y, z forms a triangle. Aina, your mic is not working.
Hello.
Aina, your mic has problem. Yeah. Somebody else? How do I write if there is a triangle x to y, y to z? There is a triangle between it, vertices x, y, z. How do I write?
Sir, it could be cyclic or it should be
It should
acyclic
be,
one.
yeah, it could be acyclic also. So for instance, there could be an edge from x to y, then y to z, and x to z. So that doesn't form a cycle. How? Fast. How? It's not a hard question. So first of all, how do I write a predicate? Undirected edge, u edge of xy. That means that if there is an edge from x to y or there is an edge from y to x, how do I write that? Somebody? How do I write if there is an edge from x to y or y to x? First, I could write if there is an edge from x to y, I could write it as that is true. Yeah, undirected edge xy is true if there is an edge from x to y. That is true. I could write another rule xy if there is an edge from y to x. Okay, I have these two rules. Now, therefore, yeah. So if there is an undirected edge from x to y, if either there is an edge from x to y or there is an edge from y to x. Now, in terms of undirected edge, how can I write has triangle? Hello.
so we can just have all the three undirected edges in the hash triangle definition.
Yeah. So I can write u edge of xy, u edge of. You remember, comma is and y z, and u edge of x. Okay. So that means this can also be written as this above rule u edge. I can also write it as if I have. I can also write it as u edge of xy is edge of xy. I can, the semicolon is actually or operator. Comma is and, semicolon is or. So I could also write it as edge of yx. So this has this is Yeah. Okay. All right. Now let's try to write one more exercise.
Sir,
Yeah.
sir, can you explain the alt reach part again? What happens there? Why is the stack overflow and which
Yeah.
side?
So that's what we are going to. That's what we are going to. So in order to understand this example, why reach works but why alt reach fails. To understand that, we should understand how Prolog is trying to satisfy the rules, satisfy the query. Yeah.
Yes, sir.
It is how Prolog is trying to satisfy the query. That's what we are going to next. Okay. So let's go to the slides. This is, yeah. Now this is one thing. Okay. So you remember all this from last time. That's okay. Okay, so let's review how Prolog program looks like. A Prolog program consists of a collection of facts and rules. A fact is a predicate terminated by a period. So identifier, then term 1 up to term k. And facts make assertions. Elephant of Mary, taller than John Fred, parent of X. Note that X is a variable. X can take on any term as its value, so that the facts asserts that every value of X parent is true. Okay. Yeah. And this is about rules. Okay, so let's come to operation of Prolog. So a query is a sequence of predicates, predicate 1, predicate 2 up to predicate k. That's what we all the time give as a query. Okay, and then Prolog tries to prove that this sequence of predicate is true using the facts and rules in the Prolog program. In proving the sequence, it performs the computation you want. Okay, all right. So if I have these rules: elephant of Fred, elephant of Mary, elephant of Joe, and then I have the rules for animal of Fred if animal of elephant of Fred, animal of Mary if elephant of Mary, animal of Joe if elephant of Joe. In query, if I give the query animal of Fred, animal of Mary, animal of Joe, then what Prolog is going to do, it is going to find these elements either as facts or as detected from the rules. Okay. Okay. Starting with the first predicate P1 of the query, Prolog examines the program from top to bottom. So I input a query and I have the program. It takes the first element, first rule of the first predicate of the query. Prolog examines the program from top to bottom. It finds the first rule head and fact that matches P1 and then replaces P1 with the rule body. Okay. So for instance, if I have the rule P1 if Q1, Q2, Q3, and if my query is P1, P2, P3, what does Prolog do? Prolog takes P1, scans the program from top to bottom. So in this case, there is only one line, and it finds P1 matches this predicate matches this predicate. So it is going to replace P1 with this entire thing, Q1, Q2, Q3. Okay. And so now what is the resulting query? Resulting query is Q1, Q2, Q3, P2, P3. Okay. And now in the next step, it is going to take this Q1 and then scans the entire program and so on. All right. So it finds the first rule head or fact that matches P1, then it replaces P1 with the rule body. P1 matched as fact, matched a fact. We can think of facts as having empty bodies. So P1 is simply removed. The result is a new query. So the in what is says that if P1 is a rule is a fact, then it is already satisfied. So I can just remove it. Yeah. You remember I told you that P1 dot is same as P1 colon dash dot. That means it is trivially satisfied. Okay. So in this case, if I have this elephant of Fred, elephant of Mary, elephant of Joe, and this query, and if I have the query elephant of Fred, animal of Mary, animal of Joe, first you take animal of Fred, scan the entire program, you find there is a rule which says that animal of Fred is elephant of Fred. So according to our rule, I'll just replace animal of red by elephant of red. So it becomes elephant of red, animal of Mary, animal of Joe in the first step, in one replacement. Next, I take the head of this elephant of red, scan the entire program, immediately find that it is a fact. So therefore, I can remove this. So I remove elephant of red. So I get the new query, animal of Mary, animal of Joe. Then I take animal of Mary, scan the program, find elephant of Mary is there, replace elephant of Mary, animal of Mary by elephant of Mary. So I'll get elephant of Mary, animal of Joe. Then I replace, then I scan with animal of elephant of Mary, find that it is a fact, and then remove that. So I get animal of Joe and so on. And I get elephant of Joe in the next step. And I replace elephant of Joe with empty query and I get empty query. Once I get empty query, Prolog will simply say true. Okay. So that means it's a query where nothing needs to be returned. There is no unification to be done. So it just returns true. That means the query is true. Yeah, is that clear?
Yes, sir.
All right.
Sir?
Yeah.
But suppose in this example only,
Mhm.
if there is another statement at last, animal of red, if not element of red, not elephant of red, means the fourth line opposite of that. Element,
Okay.
animal of red implies not elephant of red.
Yeah.
Then it will not follow that, na?
It will not follow that. And in fact, the point is that in Prolog, you don't have negation. Okay. You remember I told you that in the last class, I told you that all Prolog rule facts are horn clauses. You remember this?
Yes, sir.
Yeah. So the meaning was that every Prolog clause is a disjunction of literals in which at most one literal is positive. So this one is actually negation. So this is actually equivalent to elephant of red implies animal of red, which is same as negation elephant of red or animal of red. Now in the statement which you said, it will be animal of red, negation elephant of red implies animal of red. So that will be actually elephant of red or animal of red. Okay, such a rule is not there in standard Prolog, but there is a certain kind of negation called negation as failure. We'll come to that later. Okay, so for the moment, when you think about Prolog program, you think of them as there is programming with no negation. There are only conjunctions and disjunctions and no negations. Okay.
Okay.
All right. So, okay, if this process reduces the query to empty query, Prolog returns yes. However, during this process, each predicate in the query might match more than one fact or rule. That is true. Yeah, because in the example which we wrote, we have two predicates x for xy. So if I ask reach of if I have a query reach of AD or AA, then I could, if I have a query like this, then it could match two rules, but I will go with the first rule. Okay. So from here itself, yeah, let's, but here there are variables. So variables complicate the matter. That's what we are coming to. However, during the process, each predicate in the query might match more than one fact or rule here. Prolog always chooses the first match it finds, then the resulting query reduction did not succeed, i.e. we hit a predicate in the query that does not match any rule head or fact. Prolog backtracks and finds a new match. So what does this mean? This means that if I type in reach of AA, then what it is going to do with reach of AA is that it is going to substitute X with A, Y with A. Yeah, we will come to see how variables are handled in a few minutes, but for the moment, just it will just substitute A with X and A with Y. And now I have two rules. Both of them are reach AA. It will first take this one and try to substitute there, tries to satisfy that. So in this case, AA does not succeed. So it will abandon this rule. So it will backtrack. Okay. Backtracking means that you go ahead with one rule and then you come back and you try with the next rule. That's what my backtracking means. And then it will continue with this. Okay. And yeah. For example, if I have an antiter of red, animal of red is elephant of red, and animal of red is antiter of red. I have two facts. I have a fact antiter of red, and I have two rules, both with starting with animal of red. Animal of red is elephant of red, animal of red is antiter of red. And if I type in animal of red, it will try to satisfy, first take elephant of red, and that becomes the query elephant of red. But elephant of red is not a fact, so it doesn't reach anywhere. So prolog comes back, tries the next rule, animal of red is antiter of red, and then it goes and becomes antiter of red, and in which case it results in empty query, and then the query is satisfied. That is what we mean by backtracking. Okay, backtracking is an important concept, and most of the prolog system will work on this based on this rule, backtracking. And yeah, when we write the functional program for n queens, for instance, eight queens, we had backtracking as part of the program. We wrote that backtracking as part of the program. Here, you don't need to do that. Prolog will automatically do the backtracking. Okay. Backtracking can occur at every stage as the query is processed. All right, let's look at this program. So I have P1, the rule P1 if A1, or P1 if B1. So P1 can go to two subqueries, either A1 or B1. Similarly, A1 if C1, C1 if D1, and C1 if D2. Similarly, B1 if E1, and you have the only facts are D3, E1 and D3. Okay. So first prolog starts with P1. Now what happens? Starts with P1. How does this program proceeds? So it starts with P1, and the first rule is A1. So it tries A1, and the first rule of A1 is C1, and it goes with C1. Now it goes with D1. C1 is replaced with D1, but D1 does not have any corresponding rules, so it backtracks. So it is in C1. Now in C1, the next rule is D2. So it goes with D2, and now D2 also is not a fact. So it goes back to C1, and C1 has nowhere else to go. So C1 goes back to A1, and A1 has no other rule to try. So it goes back to P1. Now P1 is next rule is B1. So it goes to B1, and B1's next rule is E1, and E1 is a fact. So it goes with E1. Okay. So that is how backtracking happens within a program. Is that clear? Yeah.
Yes, sir.
All right. With backtracking, we can get more answers by using semicolon. So if you add the extra rule, B1 goes to D3, and then you get E1, and then if you type in colon, then it will show you D3 also. Yeah, it will also say, it will go backtrack and find the next rule which satisfies this. Okay, those are the alternative unifications. Anyway, I've been talking about this unification thingy. Now let's try to understand what is unification. So far in these queries, what is special is that what you are actually querying is this is a ground term. while reach of AX is a non-ground. Okay. So what do you make ground term and non-ground term? So what is the difference between this term and this term? Yeah, Saina, yeah. I assume that you are saying that this has no variables, this has a variable. That is true. A ground term is a term which doesn't have any variables. Okay. And a non-ground term is something which has a which has a variable. Okay. Now, most of the queries to Prolog systems are non-ground terms. You are not simply interested in finding if a query is true. Sometimes you want to find if a query is true, but you want to perform some computation with. If you want to perform some computation with Prolog, you will like Prolog to return you the answer, which if you put in a query and Prolog to give you the answers for which the query is satisfied. Okay, so that's what we want in the next step. Yeah. So we want Prolog to find out values for which a non-ground term is satisfied. Okay. Now, for instance, you could imagine that Facebook, if you have the Facebook system can be modeled like a Prolog system. You have all kinds of predicates like friends, went to school, yeah, has friend, all kinds of things. And if you are searching for a person, you can specify a query in which you can find all persons who has gone to some school from this year to this year and has a friend, some 3 common friends with you and so on. But Facebook does not use Prolog, of course, because their search is not that great. In fact, it is very difficult to find a Facebook. I mean, to find some answers. I mean, yeah, the search is not good. That is because it doesn't use any expert systems. I mean, primarily because it is a large system, so they may not find it very useful, might find it very worthwhile. Okay, so we want answers to non-ground terms. Yeah. So operation with variables. Queries are processed as before via rule and fact matching and backtracking. But now we can use variables to help us match rule heads or facts. So the operation with non-ground terms is also just like in the case of ground terms. But now there is an extra additional effort you have to put in. That is what is called unification. Okay. A query predicate matches a rule head or fact, either one with variables if the predicate name must match. So elephant of X can match with elephant of Fred, but can never match with anteater of Fred. Okay. So if my query is elephant of X, then it must match, if it can match with elephant of Fred for X equal to Fred, but it can never match with anteater of Fred. It's quite obvious. Once the predicate names arity of the predicates must match. Not only the predicate names must match, their arity. Arity, I already told you how many arguments a predicate takes. That's what is the arity. So in this case, the elephant has arity 1, and it also has arity 1. So once the predicate names, once the predicate names, yeah, there is something wrong with the sentence. So not only the predicate names must match, the arity also should match. So foo of xy can match foo of Anne Mary, but match foo Anne or foo Anne Mary Fred, but cannot match foo Anne or foo Anne Mary Fred, because this has arity 1, this has arity 3. So arity 2 can only match with arity 2. Okay. All right. So that's quite obvious, whatever we said. Now, a query predicate matches a rule head or fact, either one with the variable safe. Predicate names and arities match, then each of the k terms must match. So we are trying to this process. So I have I have a rule head from my query, and I have a rule head in the program. Okay, it's either a fact or a rule head. Now these two things I'm trying to match, and if when I'm trying to match these two things, what I'm trying to match is not try to match this one to this or this one to this, but I'm going to try to find a common solution. Yeah, let's see if there are some examples. Okay, so for instance, if I have my query is f of xa, no, that doesn't work. There are no good examples here. Yeah, let's so if my rule head, first rule head is f of t1 to tk, second rule head is g of s1 to sn. Whatever we said so far is that f and g has to be the same identifier. F and g should take the same number of arguments, so k has to be same as n. And now what we are going to try to do is that we are trying to match each of the t1 with s1, t2 with s2, and tk with sn. Okay, that's what we are trying to do. Are you following me? Hello.
Yes, sir.
All right.
Yes.
If the predicate names and arrays match, then each of the char times must match. So for foo of t1, t2, t3 to match foo of s1, s2, s3, we must have t1 matches s1, t2 matches s2, and t3 matches t3. S3, it should be S3. It should not be T3, it should be S3. During this matching process, we might have to bind some of the variables to make the terms match. Okay, so what we mean by bind? What we mean by bind is, so imagine I'm trying to satisfy reach of AX. Now I take this rule does not satisfy. Let's imagine this rule is the one which I'm trying to satisfy. So reach of AX, I'm trying to match with reach of xy. So A must match x. This is a separate variable. This must match y. Okay, this x and this x are obviously not the same. They're different. They are treated to be different variables. Yeah. And then this, whatever value I am assigning for this y, throughout this query, it should be the same value for x. Wherever y is true, so in this case y is here. This x matches this y, and this x should match with this y. Okay, that's what we mean by bind. It's not very complicated, but let's move ahead. During this matching process, we might have to bind some of the variables to make the terms match. These bindings are then passed on to the new query consisting of the rule body and the leftover query predicates. Okay. Now Now how do variables match? Two terms with variables match if both are constants, identifiers, numbers, or strings that are identical. So if I have two variables, two terms, then if they are constants, then they should be identical. If one or both are bound variables, then they must match if what the variables are bound to match. Is that clear to everybody what this last sentence means? If one or both bound variables, then they must match if what the variables are bound to match. Is that clear? That means that if I have two variables and they are already, while matching the process, while the unification happens, whatever these variables are already bound to, they should match. Okay. X and Mary, where X is bound to the value Mary, will match. X and Y, where X is bound to Mary and Y is bound to Mary, will match. X and Anne, where X is bound to Mary, will not match. That's an example of this sentence. I hope it is clear. I mean, it's not very complicated what is going on. It's like naturally, if I give you two terms and ask you do these terms, is there a way in which you can try to say that these two terms are the same? Then this is a procedure you will apply. Okay. One of the terms is an unbound variable, then they match and we bind the variable to the term. X and Mary, where X is unbound, match and make X bound to Mary. X and Y, where X is unbound and Y is bound to Mary, match and make X bound to Mary. X and Y, where both X and Y are unbound, match and make X bound to Y. Any questions? Any questions? All right. Let's try to understand. Maybe one more slide and then we'll go. Okay. Variable matching unification. If the two terms are structures, T is equal to f of T1 to Tk and S is G of S1 to Sn, then these two terms match if the identifiers F and G are identical. They both have identical identity. Each of the terms Ti and Si match recursively. Example, date X May 1900 and date 3 May Y will match where X is bound to 3 and Y is bound to 1900. That's the process we call unification. Okay, it's not just that you're trying to match one way, you're trying to match both ways. Okay, equal 2 plus 2, 3 plus 1 and equal X plus Y Z match and make X bound to Y, X bound to 1, Y bound to 2 and Z bound to 3 plus 1. Okay, now this is an example which is crucial to Prolog. But if you just say 3 plus 1 in Prolog, it is not same as 4. 3 plus 1 is 3 plus 1. If we want to say that 3 plus 1 is 4, then you should use the is operator of Prolog. Okay, so what does that do? That evaluates terms and finds the value in the underlying Prolog system.
It's 11 o'clock.
Okay, date FXA May GAB and date Z May GYQ match and make Z bound to F of XA, Y bound to A, and Q bound to B. Okay, so what happens here? I have this variable Z here. I have the term F of XA here. So if I want to unify these two terms, what I'll say is that Z is F of XA, May is May because they are constants and they have to be identical. G of AB is J, same as G of YQ. So therefore Y should be A and Q should be B. Okay. Not we can bind a variable to a term containing another variable. The predicate equality shows what Prolog unifies. Okay. All right. Let's do an exercise. Which of the following are unifiable? X and the term F of AB. So there is only one way you can make this true, where X is nothing but F of AB. F of XA and G of XA. Why these two things don't match? Why F of XA and G of XA does not match? So I think Saina said that F and G are identifiers. And if identifiers have to match, they have to have the same name and same identity. So, but here they have the different names. One is F, one is G. So therefore they are not identified. What about 3 and 2 plus 1? This is exactly the reason I said 2 plus 1 is a different term than 3. 2 plus 1 is 3 when you evaluate this expression. So to evaluate the expression, you should use a Prolog operator is. So if you write 3 is 2 plus 1, then it will be true. Okay, so otherwise they remain different. Book of X1 and book of Z, why they don't match? Why book of X1, X comma 1 and book of Z?
Arity is different.
Arity is different. Okay, now list. We didn't look at list, but Prolog list following Lisp is the same idea. So list in Prolog is constructed using, can be pattern matched. So if I write X, so this bar operator is like cons of Lisp. Okay, so if I write X bar T, then if I give you another list Z, they unify. Z. Okay. X bar T unifies with the list Z, where X is the head of the list and T is the tail of Z. What is head and tail? What is head and tail of a list? The first element is called the head, and the rest of the list is called the tail. Okay, so when you make the cons in Lisp, you take an element and then you take a list and you cons with the head with the tail, and then it becomes a list. Okay, so if I have 1, 2, 3, and if I have X, Y, then X becomes 1 and Y becomes 2, 3. Okay, when you unify. Similarly, A comma B comma X and Y comma 3, 4. This does not unify. Why this does not unify?
Nested list.
Sir, 3 or 2 elements.
3 or
3 and 2 elements.
no, 3 and 2 elements is not the reason.
Second element is not matching.
Pardon?
Second element is not matching.
Exactly. B is a constant, 3 is a constant. Okay. So if I want to unify these two lists, Y will match with A. That's not a problem. X will match with 4. That's also not a problem. But B cannot match with 3. That's the reason why you cannot unify these two elements. Okay. Okay. What about A with X and X with Y? And the reason is because if I want to match these two things, A bar X, A is an element and X is a list. Okay, so just like in Lisp and in most programming languages, you have this notion of cons. So A is an element, X is a list. So here, if I want X to unify with A, so I'll get X equal to A. Now, therefore, I'll get A bar A, and that will not match with a list. Okay, so A bar A is not a valid list. It's not a list. That's the reason. X equal to A, Y equal to A is an improper list. X of AB, F of ZY. Why they don't match? Why they don't unify? F of X of AB and F of ZY. We don't in Prolog, you don't unify with predicates. Okay, the unification happens at the level of objects. Okay, so here, if I want to unify X of AB, okay, X is an identifier. So this kind of unification is not allowed in Prolog. Okay, in a sense, in Prolog, you have all the variables are representing objects, not identifiers themselves, not predicates. Now finally, X bar, Y bar, Z, and A, B, C, D. So this thing associates to the right, bar associates to the right. That means that X bar, Y bar, Z, you will read it as Y bar, Z, and then X bar. Okay, so you will put a bracket here after, before Y and after Z. So therefore, X bar, Y bar, Z, you will unify X with A, Y with B, and Z with CD. Okay. Okay, so I think we have explained how Prolog works. Unification, goal-directed reasoning, rule outing, DFS, and backtracking. When let's do it in the next class. Query answering. And now we can go back to our example. Why is it the case that if I write it this way, this was our example. Why is this one works and this one does not work? Can somebody explain why this way of writing works and this way of writing does not work? The answer should be here. The above is problematic. Why? Here is the correct solution. This is exactly the solution we are at. The reason is if I try to start unification with path of xy with path of xz, what happens is that it goes in an infinite loop. I try to first path of xy, and then I tries to find an z says that path of xz. Yeah, and then it goes on an infinite loop. Okay, and that's the reason. Now let's try to write some examples, some sample programs. Let's try to write factorial. Okay, factorial of, I want to write factorial of 0 is 1. Okay, factorial of 0 is 1. Now factorial of n x if n1 is n minus 1. So I'm going to write a factorial program. I write factorial of 0 is 1. That's the first rule. Now I am going to write factorial of n is x if n is greater than 1. Okay, n1 is n minus 1. Okay, so I'm going to introduce a new variable n1. So first of all, I said that n is greater than 1, and I'm going to introduce a new variable and say that n1 is n minus 1. I have to use the is operator because otherwise n1 and n minus 1 does not unify because of the reasons we said. N minus 1. Now fact of n1 y and x is y times n. Okay. Factor 5 Saina is trying to say something, but
So n1 can only get to n. There is no base case.
there is no
Base case.
factor of 0 is 1, no? That's a base case.
So but n1 can only get to n. It can never get to 0.
Ah, okay. Yeah. All right. So that's factorial of 5 is 120. Can you write Fibonacci? How do we write Fibonacci? Can you try? How do we write Fibonacci? In fact, this program, if you write in Haskell, it is exactly the same program. Yeah. Instead of this one, you will write equality, and rest is almost the same. Yeah, you don't have to write, instead of is also you will write equality. And it's not just Haskell. You write in Scala, or you write in any of the, or F sharp or things like that. It will be the same program. Yeah. How do we write Fibonacci? So we write fib of, let's imagine the 0th Fibonacci number is 0. The first Fibonacci number is 1. And now Fibonacci of n x is, n has to be greater than 1. And you write n1 is n minus 1. n2 is n minus 2. And you write fib of n1 x1, fib of n2 x2, and you write x is x1 plus x2. Okay. So what is going on here? You write the rule Fibonacci of 0, 0 is true. Fibonacci of 1, 1 is true. Fibonacci of nx is true if n is greater than 1, and n1 is n minus 1, n2 is n minus 2. And you try to satisfy fib of n1 x1, fib of n2 x2, and whatever value for which this is true, you get x1 and x2, and you say x is a x1 plus x2. So if I write fib of 0x, I'll get 0. Fib of 1x, I'll get 1. If I write 2, I'll get 1. If I write 3, I'll get 2. And if I write 4, I'll get 3. Okay, and so on. Is there some other way we could write? What is how much time will it take to write compute Fibonacci this way? It will take exponential time. Can you write exercise? So is the above Fibonacci takes exponential time. Try to do it iteratively. Yeah, this is a technique which you have already learned. Write a function reverse. Is ordered. That takes. I will pause the exercises separately. Okay, try to do only this now. Then I will post some more exercises. All right. Thank you.
Sir, I have one doubt.
Yeah, please.
Sir, in that slide where we were doing unifications problem,
Mm-hmm. Yeah.
not this one.
Yeah.
So, sir, can you explain the last fourth?
Last this one and this one, or just this one?
Last fourth.
A, B, X,
This
Y, Y 3, 4.
yes, sir.
So I'm
Yes,
trying
sir.
to unify ABX and Y 3, 4. Okay, so if I have Y bar 3, 4, Y is an element and 3, 4 is a list. Okay, and here also I have A, B, and a list. So it is possible to unify them provided Y goes to A and BX matches with 3, 4. Now BX matches with 3, 4. If BX matches with 4, so that's also not a problem. But B cannot match with 3 because B and 3 both are constants. And two constants unify only if they are identical.
Okay, sir.
Yeah. All right. Okay. So I will try to give you some more list problems. And then, yeah, we will try to do that n queens and all these things once more. Okay. It should be easier to do in Prolog. Okay. Thanks a lot. Bye.
Thank you, sir.